Well, welcome. I hope your weekend was wonderful. Today's just a short review over what's coming up on the exam. This is a fun review because I haven't written it yet, so I can say anything I want. That's awesome. This is posted where the exams are posted. It's called Quiz 2 Study 15. Make sure you get the one that's for this year and reload, because I updated this a couple of weeks ago. The first, from a format standpoint, it's completely open book, open notes. You can have a handheld calculator as long as think about somebody sitting in front of you. Okay, if you can read the screen of the person in the next row, the screen's too big. But if the screen is small and hard to read other than yourself, that's the right kind of calculator. And all you need is multiply, divide, subtract, and add. Maybe logarithm. So having a calculator will be helpful. Let's see what else. There's a lot of stuff in the book. You may bring it. I would suggest you print out your SCH files for 5, 6, and 9 because the exam is over 5, 6, 7, 8, and 9, and I'm liable to assume you know how to do lab. Okay. There are certain things that you can sort of guess what I might ask. SSI, A to D, fixed point timers, and analog circuits. I want to spend most of my time on analog circuits today. Okay. Okay, it's format. Here, it's just like other exams. There's a boatload of old exams posted on the web. People have taken classes from me know, does it help to look at old exams? Yeah, I see some shaking heads. Yeah. Do you ever find the question I'm asking on an old exam, by the way? Yeah, not on purpose is the answer to that question. Not on purpose. I don't intentionally use the same question, but I'm going on 62 at the end of this month, and so I may make a mistake, and I may ask the same question. But I ask very similar questions, okay? And so you can get a flavor for what an open book test looks like in the world of Valvano by looking at old exams. But there are no communication, there are no data sheets in the exam. It's open book. I expect you to bring the book. And so we'll talk about what you need to be able to do in general in a second. So any questions on the format? 50 minutes is probably too long. I haven't made it yet, but I'm guessing it's going to be too long. I've always wished I'd make easier exams to grade, but it never seems to work out that way. All right. As you know, I allowed you to use TivaWare for some stuff in labs, except for what you were trying to learn in that lab, and so you will find that I won't let you use any TivaWare on the exam, because it's just like, just give me what I want without me knowing how to specify what I want. But you don't have to know the definitions. Clearly, I'm assuming standard definitions, and I'm really pretty lenient about the syntax. If you forget the /R and it doesn't compile, it's not an issue with the exam. So this is sort of an overview of the I/O devices I expect you to know for the exam: periodic, timer periodic, edge triggered interrupt, input capture, SSI. Basically, the lectures up to and including when we started on, but not the motor. So if you see from a lab standpoint, all of the stuff that we had in labs 5, 6. Now 7 and 8 is a little hard for me to examine you on because I don't know what your project is, and certainly everyone else doesn't know. So when you think about 7 and 8, it's a focus mostly on the power systems, the crystal, the regulators, etc. And then, you know, there's a reading in the book. So these were the what you should have read when you did Lab 5, okay, which was the D to A and the edge-triggered interrupts and the DAC and timer interrupts, etc. And then in Lab 7, focus on capacitance, the regulators, interfacing, SSI chips, and then lots of stuff in Lab 9 that you just finished. What's a resistor, what's a capacitor, op amps, instrumentation amps, circuits, threshold detectors, analog filters, the A to D converter. I didn't really talk about the MAC, so I probably won't ask it. But data acquisition systems, transducers, the Nyquist theorem, not the Valvano principle, clearly. And the design process. Okay. Overview questions on, is it on the exam, is it not on the exam? So with a focus on labs 5, 6, and 9 would be my advice. Then from a study standpoint, I've told, I announced it on Canvas a couple of weeks ago, but I have this suggestion for how to study. Okay, sort your understanding into categories, hard and easy. Okay, okay, and then I want to focus on the hard. And what I want you to do is find old exam questions and do it without looking at the answer. This is the key part. It'll poison you. Download the answers if you want and print them all out. You won't find the answer there. But if you look at the answer, you're going to be poisoned, okay? Because it'll go, that's easy, okay, without looking at the answer. And then do either show it to me, come to office hours, or your TA, or your lab partner, or your study guide, your study buddy, then show it to somebody. So an effective way to study is to sit around doing exam questions, and when you're done, before you look at the answer, show it to somebody, okay? And that'll be a measure of how good you are, okay? Now, you don't have to do all the, you can, if you'd like, you know, you can sort of do one of those expected values and look at most likely. If you want to maximize your study time. Okay. All right. All right. So that's what this list right here is for. Okay, is a list by topic of old exams. Now, if you find SPI and setting up the timings and etc., if you find that easy, don't do very many of these. Okay? Do a few. If you find analog hard, well, then do a bunch. Okay. The other advice is to work backwards in time. Okay. Because some questions really shouldn't have been here in the study guide, like who cares about how to initialize the 9S12, okay? If you see a 9S12 question back in the old ancient dinosaur days, you know, just re-ask the question with the arm, I guess. But, or somebody needs to take that out, right? Because that's stupid. Nobody cares about the arm. All right. Okay. Fixed point, I like it, as you know. And then there's a lot of ways to ask interrupt questions, but remember this is an open book test, so you can write code. One of the one of the easiest ways for me to ask a question is to give you code out of the book and ask you to change it. That's an easy question for me to grade. And in my defense, a very typical use case for how one programs embedded systems. You know what I'm going to ask about capacitors, right? I expect you to know some things. All right. List me the things I want you to know.
Impedance is 1 over j omega.
Yeah. Z equals 1 over j 2 pi f c. Yep. That's it. I want that. What else do I want? Or 1 over j omega c, right? What else do I want? Yeah, sure. Now, which is which? Do you remember? Is it? All right, I could ask you that. What else can I ask you? These are good questions.
DC behavior.
The DC behavior, right? So if you put in I have to give you a resistor, right, for this to be. Oh, maybe you were asking a different question. Sorry. Okay. I want the step response. If this is V in, what is V out? Right, and this has to do with the time constant being RC. Could give you this one. And that is going to what I guess what the question you actually asked, what said was, the DC is it's an open, and then the very large AC it's a closed. Sure. Another question I could ask has to do with lab 6, by the way. What's a capacitor question in lab 6, 7, and 8? You came to my office and got a bag, okay? I could ask you what this is. So excuse my what is it? Actually, electrolytics look like this. You probably didn't get an electrolytic in my office. Electrolytics could look like that, but the trick is the one leads longer than the other. What does that mean? It means it's what type of capacitor. These are the tantalum. This is the tantalum capacitor, and I didn't really give you any electrolytics, but so the tantalum, and big number, big voltage. That's a Urabali thing. Yeah, it's a plus side. And as opposed to this one, with this equal size, okay? That's a ceramic, okay? I could ask you this, 2, 3, 4, what is it? I can ask you that one, by the way. That's probably a nasty question. What is it? It's ceramic, but what value, right?
0.23 microfarad.
23,000 picofarads is what it is. Okay. Well, I'm sorry. Did you say 0.23?
Micro.
Yeah, that was the right answer. 0.23. Another question is, why do we use a ceramic versus why do we use? So I will ask you one of these capacitor questions. All right. Okay. Questions? The other thing I prepared for today was, do you remember what we called circuit design in 445L? the way in which a circuit designed for computer scientists. Remember that? I used that word a couple of times. What I mean by that is the world is full of followers, and occasionally, once every 10 years, a leader comes by. Okay? Hopefully one of you people are leaders. Okay? What that means from a circuit standpoint is you're not designing anything. What you're doing is choosing the right shape and modifying it. And that's especially true in this class. So let's just go through the labs. In Lab 5, what were they? Sorry. The DAC. Okay. So from a standpoint, I could give you a different DAC, by the way. Okay? I could give you a different DAC, and you had to find the SSI. Okay? And the key point in configuring the SSI were two magic words. And what were they? Set up and hold. Okay? We're going to look for the set up and hold. And that is going to specify the edge around which data is being transmitted. Okay? That's how we're going to figure out the mode. And then we're going to match it to one of the modes in the book. Okay, so you go to chapter, okay, this is serial. So here it is, figure 717. So you got a bookmark on that. It's got the modes, okay? All right, and then the other issues associated with the DAC are things like range, resolution, and precision. Okay. Sampling, output sampling rate. Okay, so the Nyquist theorem applies. Okay. What other circuits do we have in Lab 5 from a modular standpoint?
The amplifier.
Sure, we had an amplifier. Okay. Okay, and there were some capacitors on here. So what could I adjust? Think about this circuit, the amplifier. What could I change? I could change the resistors, and the resistors would do what? Could change the resistors. Would change the gain. So I could give you a different gain. I could ask you the maximum power, right? Power is just I times V, okay? Or power equals V squared over R, okay? How does that matter? All right, that matters on the power line that I put here, right? 5 volts, right? A 5 volt power is how much louder than a 3.3 volt power? All right, what's the ratio of the powers? Right? It's a ratio of P good versus power bad, or the ratio of P loud versus P soft is what? How do I fix this equation? Square them, okay? All right. What can I do with this cap right here, by the way? I can adjust that cap on you. Its purpose? A cap in line with the analog signal is what type of thing, by the way? That's a high-pass filter, okay? And its cutoff frequency is 1 over 2 pi RC, okay? Where this R and that C. All right, so one more. One more module in Lab 5. Shunt diode, sure. I always forget which way it goes. Something like that. R1, R2, R3, right? So this is the V reference right there. So why do we choose R1? Why do we choose R2? Why do we choose R3? Questions on Lab 5? Circuits? Okay, let's do some more. How about your circuits in Lab 6? Now I can ask it. There were some. 6, 7, 8. Everybody's had what? Everybody's circuit had what?
Power.
The power, right? You have some sort of input and a module, and then we have output. Plus 3.3, plus 5. Oops. Okay. You will notice that, okay, so this is the regulator, right? That's what I'm after. I did ask the type question. I've asked that before, right? We have linear, we have buck, we have boost, and we have buck boost. Okay. An important parameter for a linear regulator is what? What are in a linear regulator, what are the things that matter? There are 3 parameters. Here's a pile of linear regulators. Pick the correct one. You want to look at 3 things. There's 3 parameters, well, there may be more, but at least 3 parameters associated with choosing the correct regulator. One of them is obvious. Well, they're all obvious, but.
Current.
Current, sure. Okay, if we call this VCC, this is the available. And what is the purpose of this current? It drives the system, right? It's driving your liquid crystal display, your processor, all your electronics need current. That's the available current for the system. What else? Sort of obvious. What?
Dropout voltage.
Oh, dropout. That's the hard one. Sure. That's a hard one. VDO. Now it turns out the boost regulators don't have dropout. They have drop up, if you like. It gets bigger. Okay, but only the linear regulators have a dropout voltage, which is the difference. So this has to be bigger. Right. The input voltage has to be bigger than the desired voltage plus the dropout voltage, which is why I tried to get you guys to use the LP2950 versus the LM2737. They're both 3.3 volt regulators, but this one's got a very low dropout. And obviously, the third one I was trying to get you to say was the voltage itself. Okay? You want the voltage. That's yourself. I'm not, in terms of an exam standpoint, I'm not real worried about these caps. Typically, you just read the values off the data sheet. I could ask you what it's for. What are the caps for?
Low pass filter.
Yeah, technically, it's actually a control theory question, and they're stabilized. They stabilize the regulator. The regulator, most regulators have built-in feedback. Okay, so if the error is off, it lets more in. If the error is too small, it lets more out. And there's a feedback mechanism going on in the regulator, and the capacitors are there to stabilize it. They are low-pass filters, so that's why it would be a tough question to ask. Okay. More circuits. To crystal, sure. I don't know what I could ask. I could ask you, why do you use C0Gs here on those 10 picofarads? I could ask you why there's a crystal. Yeah, but again, the crystal circuit is, again, we're not going to design the crystal circuit. We're just going to look it up and choose it. I could ask you why this was a bad idea. I saw this on when Mahesh and I were building. When we were building, we saw this. There was the crystal. Okay, so here's the trace to the processor. And then here was, I don't know how they did it. I don't know how they did it, but it took some doing. I came in here, I came into a via, turned blue, into here, turned red, and it went right there. That was a bad idea. Why? Yeah, I'm going to inject noise into the clock. Okay, DI, DT, VDT, all those bad things happen, cause pickup. That's a really bad thing. This would be a hard question to ask. I don't know. I probably shouldn't even show it to you. I don't know. That would be nasty for me to ask this question. Why don't we put a ground plane under the crystal? Anybody know that one? I prevented ground planes everywhere because they're really bad for soldering. But I also told you if you wanted a ground plane, don't put it under the crystal. Or if you read the data sheet, it says don't put a ground plane under the crystal. Okay. What is the nature? Okay. Let's look at okay. That's a trace. That's your printed circuit board, and I blew things up so you can. This is the copper of a trace. Okay, and the green is the printed circuit board. What did I just create? That's a capacitor. Okay, and remember we had to choose 10 picofarads because that's what stabilized. If you get 11 in there, it doesn't work. So be careful. Don't put. Now, often, this is actually a very good thing, by the way. And you heard that from that guy from Innovations, right? Let me do another one. I'm drawing a cross-sectional cutout of this is actually awesome. Absolutely awesome. This is, we have a 4-layer board here, right? Ground plane and a power plane. First of all, what's this? What's the power plane and the ground plane?
Capacitor.
Great big capacitor, which is a good thing, right? It's across the power lines. But what can you tell me about the crosstalk between this black signal and this magenta? Can't get there. So that's a 325 thing. High frequency here cannot radiate across that plane to this. Can't pick up down there. I won't ask that. But I could ask you what the crystal is for, and what the 10, why we chose 010 G. Okay. Other things that you know that are in the switches and the LEDs. All right. Let's do lab 9, not 9, yeah, lab 9. What are the lab 9 circuits? Okay. What are the lab 9 circuits? The bridge. Yeah, I'm going to call it a circuit because it's a module. Okay? It's got a V here. Okay, and it's got 4 resistors. Okay, and it's got a, let's call that Vn, and it's got a V out, which is differential. Now, sometimes the bridge, like in our case, had 1 resistor that changed. Other times, the bridge is such that all the resistors change. This one goes down, this one goes down, this one goes up, and that one goes up. Okay. But they all have this relationship between the delta R and the delta V, V out. Okay? So that's the essence of what a bridge does. What can you tell me about this? When you build a bridge,
It has to be really stable.
yeah, this is noise, low noise, because if you think about it, noise injected into here comes flying out there. All right, what else we got? What else do we got?
Circuit that generates the Vn.
Sure, we already got. Okay, fine. I don't need to redo that's the shunt diode. We had that earlier. Although sometimes I give you this just for fun. I give you a circuit you've never seen before. This one's like totally hard. Okay, no, it's like totally easy. Okay, what number is it? 03, something like that. There's a table in the book of reference voltage, of reference chips. Oh yeah, let me give you the table number. Okay, it's in chapter 8. Sometimes the index works, and sometimes it doesn't. In this case, it did work. Okay, it's table 8.5. Is a list of a whole bunch of references. These guys are like totally mindless because you just power it up and out comes the voltage. That's a 2.5 volt reference, the Ref 03. And you can buy them at 1.2, 1.25, 1.6, 2.048. Okay, that's all. What else? What other circuits are in lab 9? Okay, filter. Can I do that one next? Later? Yes. The next one in the block diagram is instrumentation. Okay. Yeah, there's a formula for this, for the relationship between the gain and this RG. Yeah, you might want to, you don't have to memorize it, but you might want to have a bookmark. That gain is equal to 200K over RG plus 5. And that's for an INA 122. You remember the reasons it must be differential. It must be, and then any one of large input impedance, large gain, or good common mode rejection ratio. Okay. Then we got the questions on that. That's pretty simple. That's a block. You just pick the R. Yeah.
So is this just a op-amp with some extra? Like
No.
the gain circuit's already in.
Okay, so he said, what is it? Yeah, it's actually expensive, by the way. Look up how much it costs, by the way. You got it for free, but it's actually a very expensive chip. From a block diagram standpoint, it sort of looks like this. And this is actually RG. And this is, again, beyond the scope of 445L, but this is what's inside of it. And this guy here is laser trimmed. To get maximum common mode rejection ratio. That's typically how this happens. You can't build this out of parts. It'll be really, really crappy. Okay? But that's essentially what's going on in there. And so you can see that it had a gain of 5, and then the rest of this is the 200K. I'm not going to ask you that circuit. But if you don't own one, you got to build it. That's crappy. Okay. Now we got the filter. Okay, this is going to be the plus terminal. And then this guy here. C, 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 R, R. And you may want to just find the bookmark in the, this is page 410. Page 410, figure 825. Because the design process is pretty straightforward. You pick your cutoff frequency how? Rule of thumb is going to get you all the points on the exam. By the way, the purpose of this filter is to do what? Two purposes of this filter are what and what? It is a low pass, but why? Anti-aliasing. And it improves signal-to-noise ratio, right? And so to make it anti-aliasing, to get all the points on the exam, what cutoff frequency should I choose? 1/2 FS. Okay, now if you want to make it bigger than 1/2 FS, I'm fine. Or less than 1/2 FS, I'm fine. But you know, I meant less than, not bigger than. Okay, but that'll get you real close in life because it will reject above 1/2 FS. And so the steps are to divide the capacitors by 2 pi FC. Find a factor R equals R times X and C equals C divided by X to get a standard C. And then you can pick a standard R. That's the sequence. All right. I would, and you will see that this template here where this can be as many as you want. And this circuit is, this design, I did a bunch of these in class, but I'd encourage you to have a look at that again. This is figure 815. One more. That one and this one. Okay, what are these two circuits? These are threshold detectors, and threshold detector with hysteresis. All right, so questions on the exam? We're going to talk about stepper motors on Wednesday. I will write the exam according to the study guide in terms of what is listed. Try not to make up too much stuff that isn't on here. Let's see, what else would I say about this exam? The thing about the circuits, right, is pattern match. Now, labs 5, 6, 7, and 8 didn't have that high current transistor. That occurred in lab 10, so I'm going to put that one off for the final. But there aren't that many circuits that we've introduced in this class. And so I would just organize them as a way to get through the exam in a very fast way.